Okay, fresh from Chicago.
Yeah. I landed in LaGuardia, like, can people hear me if I just like talk? Okay. I'll just turn this on.
Yeah, okay.
Hello?
If you hold it.
Oh, I have to hold it. Okay, cool. Yeah, I just like landed in LaGuardia like 15 minutes ago or something like that. But I'm back. Okay, so I'm going to talk about lookup arguments, like kind of like a 10,000 foot view of lookup arguments. I'm not going to say anything specific. I'm not going to like prove any theorems. I don't think I'm even going to say anything like totally mathematically precise. But sort of in the spirit of just a 30-minute talk, I figured I would just give you a sense of like what lookup arguments are, how they're useful, and like maybe a little bit of like a taxonomy of lookup arguments as they exist now. So first, maybe I'll answer one question, which is, who am I? I'm Matej, cryptographer at Lurk. Next question, which is, what is a lookup argument? So the idea behind a lookup argument is that it's kind of an extension of the sort of interactive protocols that we've already seen, where now we're kind of giving the prover and the verifier a little bit of extra technology. So the idea behind a lookup argument is that the prover and the verifier both agree to some table of values, and the prover can then sort of use the values of that table in the course of the usual proof system. And the idea is the lookup argument security assumptions is that the prover, in using these values, or rather the verifier can be reasonably confident that the prover has accurately used the values from this table whenever he says he does. So this is a very, very broad idea. This is like incredibly vague, intentionally so, because again, I'm not going to say anything very precise. So let's see an example of this in action just to get a sense of how this could be useful in practice. So first I'm going to give you a non-example. So I'm going to give you an example of how we can do something called range checks without lookup arguments, and then I'll kind of give you a little bit of a sense of how range checks can work with lookup arguments. So first, what is range checking? So the idea is, or well, let's do range checking in a naive way. So without making any assumptions about our arithmetization, hopefully that was a word that was used already. So sort of like, I'm not saying anything about like Ponk or R1CS or other ones, or air. This is going to be sort of like, should be sort of vague enough and broad enough that it captures any of those arithmetizations. But in pretty much any ZK setting, you're going to be using a field which is going to be very large, or relatively large. Like some people talk about small fields, but even small fields are pretty big. And the idea is we want to represent uints, like uint 8 or something like that, in our circuit. And how can we ensure that something that exists in our field F is within this range, or some particular element A in our field F is within the range 0 to 255? How can we guarantee that it's U8? So you don't get to write kind of like inequalities necessarily. It's like sort of hard to make sense out of that in a proof system. So how can we write this down in terms of like polynomials and zeros of polynomials and that kind of idea? And the idea is what we first do is we introduce 8 auxiliary new variables, B0 to B7, and we add in a few new constraints. So the new constraints are going to be of 2 forms. Actually, I'll tell you exactly how many constraints. We're going to add in 9 new constraints. And they're going to be of 2 forms. The first 8 of them are just constraining the bi to be either 0 or 1. And you can do that by setting b squared minus b equals 0. So the only solutions now are b equals 0 and b equals 1. So that constrains all of the bi to be either 0 or 1. And then we add in one extra constraint, which is saying that a is actually the sum of these 7 or these 8 bi's. And the b's were chosen in some sense to be the bit decomposition of the number a. And knowing that the zeros, knowing that the bi are between 0 and 1, the only values of this sum can possibly be between 0 and 255. So that is a way of constraining a to be within this range. And you'll notice that in order to make this constraint, we've had to introduce 8 new variables and 9 new constraints, which, depending on your proof system, could be relatively costly. This example may be not so bad, but what if I have a ton of U8s in the course of my program? Or what if I have something like U32s or U64s? Then I'm going to be adding a lot of constraints. I'm going to be adding a lot of new bit values. And so I'm sort of bloating my arithmetization with a bunch of values that aren't really doing anything in terms of the core logic of the theorem or of the proof system, but it's just making the proof system even more expensive. So how can we do this with range checks? So recall what were range checks? Range checks was I'm sort of fixing a table of values at the very beginning, the prover and the verifier, and then the prover and the verifier can be confident that whenever the prover takes something, says that this is like a U8, for example, then the verifier can be confident that this is in fact a U8. It's coming from that table. And so what are we doing? We're going to start with the table of values that we want our U8 to be within, so it's between 0 and 255. And then in the course of proving whatever the prover is trying to prove to the verifier, they're going to start keeping track of all the times that they use a so-called U8. So 16, 39, 3, etc. And at the very end, the prover and the verifier are going to have to go through some interactive protocol, as most interactive protocol, or as most proof systems go. And the prover and the verifier in the course of the lookup argument are going to show that this set of queried values, f, is actually a subset of this set of fixed values at the very beginning t. And if the lookup argument is efficient enough, and if you're making, like, say, for example, a lot of lookups and a lot of and maybe the tables aren't so big, then this could be cheaper than introducing all of those new extra constraints and variables in your proof system. And so obviously there's a balancing act. Maybe you shouldn't always use lookup arguments if you're just doing a single U8. That might seem a little like overkill. But if you have like a ton of U8s or you have different settings, then lookup arguments could be helpful, because if the cost of the lookup argument is less than the cost of introducing all of those new variables, then it's going to be worth it for you. And so this is like a very simple example. This is the range checking example with lookups, and this is a particular example of range checking where you're doing it with U8s. So what if I want to do something like bigger, like U64s or U32s, or maybe even I'm working in a prime field and I have another prime field that's roughly of the same size but not quite. How do I make sure that all of these different values are going to be consistent? Well, you can, so same question. This idea of a lookup table might get a little bit too large. In some settings, the verifier and the prover actually have to literally instantiate this lookup table. They have to like sit down and maybe do something like a Merkle commitment to that lookup table. And if your field is like 2 to 256, that's not actually feasible. Like, computers can't do that. So how are we going to do that? Well, you can still do something similar. You can limit in terms of limbs that are relatively a reasonable size. So say, for example, limbs of size 2 to the 16 or 2 to the 32. 2 to the 32 is like maybe on the limit of what computers can do nowadays. And then using those individual limbs, you can still do lookup arguments where you can ensure that the limbs are within these lookup values. Oh yeah, and if people have questions, raise your hand, stop me. Yeah, don't feel shy. Any questions? Did that make sense? Does this example make sense? Is this boring? Yeah?
Sorry, when you say limbs, do you mean the same thing as like the big-end implementations that break up like a
Yeah. So like
Okay.
Yeah.
Thank you.
So if it's like 2 to the 256 or whatever, I'll have 4 U64s as my 4 limbs or something like that. Okay, so how do lookup arguments work? So again, I'm not going to say anything very precise, but the idea behind lookup arguments is that there's too many different kinds of lookup arguments to be precise, I guess is what I'm trying to say. But a common theme between pretty much all lookup arguments at this point are that you're just trying to prove an equality of multisets. A multiset is a set where you keep track of the multiplicities of however many times something appears in that set. And so, just to be extra precise, recall sets are order independent, so they're not lists, and a traditional set doesn't have multiplicities. So if I give you, like, if I write down the set A, comma A, that really is mathematically like the set A. Sets don't have multiplicities, but multisets do. And it's important to keep track of multiplicities because, say, for example, you might be querying the same value multiple times, and you want your proof system to account for that, essentially. And so a common theme essentially between all lookup arguments is that you're trying to prove an equality of multisets. And this is done by, I think maybe the only equation that I have on my slide. slides. This is done by verifying the equality of the following polynomials. And so let me take a little bit of a step back and explain what's going on here. So first, we have this big table of finite field elements, and I realized on the flight over that there's actually n plus 1 of these guys. So whatever, fn plus 1 or tn minus 1, whatever, however you're going to fix that. But you have this whole set of the lookup table, and then f is going to be the set of query values that the prover is going to use in the course of his proof system. And these mi's are the number of times that these lookup values are actually, these values are actually querying. So for example, over here we will have like 16, 39, 3, 22, 43, and 156 with multiplicity 1, and maybe like 3 appears somewhere in these dot dot dots. So maybe 3 will actually appear with multiplicity 2, and there's going to be a lot of things that don't appear. So those are going to have multiplicity 0, right? And what are you actually doing when you query? When you prove that this polynomial equality holds? Essentially, by what is it? Probably like the fundamental theorem of algebra or something like that. There's two polynomials are equal to each other when their roots are the same, right? Beziers theorem? I don't know. Is it Beziers theorem? Schwarzschild says something a little bit different. I will use Schwarzschild in a second, but I don't know. I used to be a mathematician, so I should know, but I don't know. But you have this product of the fi's and you have this product of the x minus ti's with the correct multiplicities. And saying that these two things are equal is essentially saying that all of these fi's, if I kind of go through this list of fi's, there's a way of reordering them and grouping them in such a way so that they x to the ti or x minus ti to the mi captures the number of the times fi appears on the right hand side. So for example, there's going to be some j over here which is equal to, for which tj equals fi, and this mj is the number of times fi appears on the right hand side. So I'm really belaboring this point, but essentially it really boils down to some polynomial equality. Polynomial equalities in most proof systems are things that are very natural to describe and things that you can encode in your polynomial. And then how do you prove this polynomial equality depends on the lookup argument that you're doing. Sometimes you might use a Schwarzschild type thing. Maybe you'll add like an extra round of interactivity where the verifier and the prover, or the verifier will provide some extra randomness, and you can check these two polynomials equal to each other by just evaluating at a random value. That's a little bit dangerous because what if these polynomials are very large, or is the verifier evaluating these polynomials, the prover verifying these polynomials? There's kind of a lot of levers that you can pull and adjust it to describe the different kinds of lookup arguments. But checking that two polynomials are equal roughly is, you can be relatively confident by evaluating at a random point. You can use something like a pairing-based thing where you would do polynomial commitments on either side, and you would check that these polynomials are the same by doing some pairing. The world is your oyster in terms of how you would prove two polynomials are equal. But if you were able to do that, you essentially have a new lookup argument, and you're able to use all of the benefits of lookup arguments in the proof system. Does that make sense? Okay, so lookup arguments are not new by any means. They've actually been around for a really long time. So I think it should not be so controversial to say that the idea of lookup arguments stems from this paper, Checking the Correctness of Memories, by Manuel Blum from 1991, completely devoid from the context of ZK. They were working in the setting of checking, which in the ZK context would be something like a verifier, checking the correct execution of programs. And up until this point, the kinds of programs that you could check execution for were programs where the state didn't change, where it was an immutable state, it was a pure type function. Functions without side effects. But this paper introduced new forms of programs that you could check where you could use read and write memory. So read and write memory is even more complicated than what we were really using up until this point. Up until this point, all we were saying is we have some sort of like ROM in some sense, and we're querying this random, this ROM chip for data. But really, lookup arguments are flexible enough that you can use them as RAM as well. So, or at least some of them are. And this paper introduced some new permutation arguments, things that are common in things like Plonk and like air, where you can, and they introduced the ideas of permutation arguments, and that's how they were able to check the execution of all these different programs. And concretely, what the verifier is actually checking is they're checking that when you read a value from a cell in memory, that's going to be the last value that was written to that cell in memory. And if the verifier can check that, then they're confident that the memory is not misbehaving and they can trust the execution of this program. So in some sense, like the execution of this program is kind of coming from like an untrusted prover in some sense. That was not the language that they were using. They were not thinking about it in terms of interactive protocols. But sort of in the ZK context, that's the way we should think about it. But modern lookup arguments have taken this idea and run with it. So this is not an exhaustive list by any means, but this is maybe some of the more recent ideas around lookup arguments. I think maybe some of the earliest lookup arguments are in the context of these really old style ZKVMs called like TinyRAM and things like that. So ARIA used lookup arguments to implement the RAM chip in TinyRAM. A little bit after that, Lookup was introduced to provide lookup arguments for Plonk style proving systems. And sort of from then, there was like an explosion of lookup arguments. And so Hawk was one of the early next lookup arguments, and it improved Lookup, among many other things, to have a prover cost of this, where n is the number of lookups that you do and n is the size of your lookup table. And then from there were tons and tons of lookup arguments expanding upon lookup. And so we have some people in the audience who contributed to this list. But there's Hawk Plus, CQ, Baloo, and others. And just as a comment for people who write cryptography papers, you're giving me a really hard job to actually get all of the typesetting right. I have to like look at the paper and make sure, oh, is this Fractor font? No, is it sans serif font? No, okay, I gotta, everyone uses different things. So how about we just like calm down and use regular text, okay? But even Baloo, right? Like, see, this is emphasized. That's a particular choice of the authors of the paper, and I tried to be careful when I write it out, but it is annoying. Okay, anyways, so that's just beside the point. And so in this family of work, so this is one large family of work. Another interesting family of work that's kind of orthogonal to it is this lookup argument, where you're able to prove lookups using the subject protocol. This unlocks lookups in settings where you would maybe generally not have lookups in others. So for example, in the case where your optimization is an R1CS optimization, this logup and the later logup and GKR lookup arguments were important in introducing lookup arguments for those kinds of settings. And then there's other improvements that you can do using sort of trickier cryptography. And in particular, I'll comment on this particular one. Well, I guess I didn't give it its name, but Lasso is a new lookup argument with Srinan Sethi, Riyad, and Justin Taylor. And you can avoid, the prover can avoid committing to tables in this lookup argument as long as the tables are so-called structured tables. And these are actually relatively common in use cases that we'll see in a second. So, like any proof system, lookup arguments are similar. There's not a single best lookup argument for every particular case. There's various trade-offs you have to consider when you're considering lookup arguments. Some of them is this pre-processing step of like actually committing to the table that the prover is going to use. If you're going to be using very large tables, like maybe something like 2 to the 64, maybe you would be looking for a lookup argument where the cost of committing to this lookup table is small. Maybe if your tables are relatively small, then maybe that's not a cost that you really care about. The number of lookups is maybe another cost. So like the cost may depend on the cost for the prover may depend on the number of lookups. You would hope that the cost for the prover doesn't depend on or the verifier doesn't depend on the number of lookups that the prover does. But in some of the lookup arguments, that cost does depend. The verifier cost does depend on that value. So that's something that you should worry about as well. Then of course there's proof sizes. So if you're thinking about Ethereum verifiability for your protocol, you would want your proofs to be relatively small, and other goodies that you might be interested in. So like, is this a lookup argument like homomorphic in any sense, or can you aggregate it, or can you use multiple tables? So far, I've only described lookup arguments where you're using a single table. But what if you have multiple tables? Can you sort of split your table up into multiple different subtables? And this is way too small. Oh, actually, it's not too small. But here's a table I took from the CQ paper, which just kind of, I mean, I'm not going to go through it in any sense, but like it kind of goes through. You can see the different costs for the prover. This G2. So these are all pairing-based lookup arguments. And so these G1s and G2s are just describing how many operations you have to do on the first curve or the second curve, and how many field operations you have to do. And then, so that's for the prover work. Here's for the prover size. And then the verifier work, how many pairings the verifier has to do in order to verify the thing. And then these goodies, is it aggregatable, is it homomorphic, et cetera. And there's a lot of levers you can pull, and you should kind of go through the literature. And I've included a lot of references at the end of these slides, and I'm sure there's going to be a way I can share this after the fact. If people are interested in going through the literature in any particular order. And yeah, so you should really take some time, go through the lookup arguments as they exist in the literature to see which fits your situation best. So I so far haven't described too many applications of lookup arguments. I've given one. I've given the range checking application, but there's a lot of applications, or at least I think there are. And one of which is really hot right now, is using lookups in the context of ZKVMs. And I think ZKVMs were talked about earlier, but they were? Okay, good. But there are some ZKVMs which are very lookup centric. And so two of the big ones that have been in the news lately are like SP1/Lita. It uses logup in their lookup arguments. Jolt uses lasso. And here I'm opening up audience participation if anyone wants to yell out other ZKVMs they know that use lookup arguments. I couldn't think of any, but I'm sure there are. Mine.
What is Jolt?
Jolt is a lookup argument that's based off of lasso. So there were two papers that came out almost simultaneously, lasso and Jolt. And the idea, it's a RISC-V ZKVM where, and I'll actually, there's like a few words I'll say about Jolt, but it's a ZKVM that uses the lasso. Actually, yeah, that's a good question. I'll answer it in a second. But what are, does anyone know of any other ZKVMs? I'm sure there are. Does RISC series lookups? I'm sure they do in some way. Yeah, for rewrite memory, I'm sure they have to. I don't know what lookup argument they use.
Scroll, I don't know,
Scroll, yeah, okay.
Polygon
Sure, yeah.
I don't know.
I'm sure almost all ZKVMs
Yeah.
probably have to use lookups in some form or another. I just don't know what lookups they use.
Yeah.
But these ones I do know because they're ones that I've looked into pretty carefully.
Yeah. Lydia, the old name SP1?
It's still being worked on. But SP1, the architecture of SP1 is very similar to the architecture of Lurk. Yeah. I think
So they're two separate things.
they're two separate things, yeah. But I put a slash there just to suggest that the architecture, the way they use lookup arguments are very, very similar. And so here, yeah, so SP1 and Lita both use logup or lookup arguments for different chips. So you sort of have, so these are both, or SP1 is a ZKVM for the RISC-V architecture, and you have sort of different chips for all the different kinds of operations that you would do in the RISC-V, different sort of opcodes. And Velita is similar, and in order for these chips to communicate with each other, you use kind of like a common read-write memory that's implemented in terms of lookups, in terms of the log of lookup. You have these, just to get a little bit into the weeds, you have these like extra read-write columns that you add to all of your chips, and you kind of keep track of multiplicities, and there's this extra round of interactivity at the end where you have to accumulate this log up accumulator, and at the very end of the program, it's like, is this thing 0, essentially? Does this polynomial equal this other polynomial? And if it does, then you can be confident that your ZKVM is operating correctly, and if it doesn't, then someone's trying to cheat. Jolt uses lookup arguments very similarly. They have a common read-write memory, but they also use the lasso lookup argument to great effect because they're able to actually not implement these like very fiddly bit type operations like add or XOR or shift left or shift right. You can use these, it turns out that these operations have the necessary properties to be these so-called structured tables. And so we can create these pretty big lookup tables. I mean, you're calculating, let's just think about how big it is, add. If we're adding two U32s, we have U32 here, we have a U32 here, so that's like 2 to the 64, right? So we have like a big lookup table of size 2 to the 64. This thing is never actually in practice like produced, but it's a structured lookup table, structured being something like the result is something that's easily representable in terms of polynomials. And because it's structured, we can use lookups to actually just straight up do these operations. And actually, I'm pretty sure almost all of the RISC-V opcodes are implemented in terms of lookups in the Jolt. But that's not the only piece, right? It also has a similar read-write memory that's being used so that different troops can communicate with each other. And then I'm sure there's other really cool, tricky things that are happening with different ZKVMs and how they use lookup arguments. I don't know about them because I'm relatively new, and then also like I'm very insular in the kinds of things that I look at. But if people have other things that they want to say, that's totally cool because I'm basically done. So thanks for listening.
Any questions?
Yes?
What is Lurk going to do for lookup arguments?
Yeah, that's a good question. I don't know how much I'm allowed to say, but Lurk, so far up until this point, if you've been following a little bit about Lurk, we built our whole ecosystem on top of Nova and Supernova, and we've been using we've been using folding schemes. I don't know if that's a word that's been used, but if you kind of like take a step back and look at it, it's not so compatible with lookup arguments, but there's a lot of internal work. It's very exciting. Can't really talk about it, but lookup arguments are on the way.
Wait, what is Nova, Supernova?
Yeah, okay, so that's beside this, but Nova and Supernova are these so-called folding schemes. The idea is, say I have a big program that I want to execute, and just roughly the calculus you should have in your head is that the size of the program that you're trying to execute should roughly correspond to the cost or the size of the proof or cost of the prover. But there's like tricks that you can do. And in particular, there's one trick that you can do, which is called folding, which is, which works in a very particular setting. And that particular setting is if the program that you're executing is actually just the same function operated over and over again, where you take in the input from one, spit it out, take in the input again, spit it out, etc. So basically, you're calculating some big F to the end applied to some value. And if your program is of that form, then you can do this trick called folding, where the size of the proof and kind of the verifier cost is only going to depend on the size of a single invocation of that function f. And this is more common than you would think. So for example, like a virtual machine or like a RISC-V machine, what you're really doing is you're like kind of doing the same thing over and over again. Like CPUs kind of do the same thing over and over again, right? It looks at your opcode, decodes it, and then applies that operation to the inputs, and then looks at the next opcode and decodes it, right? It's like kind of doing the same thing over and over and over again. And so it's kind of nice to be able to fold arguments together, and then the verifier cost and the proof size are not going to be dependent on how many times it's been in this operator. So it's like a very vague idea, but it's a thing that Nova, or it's a thing that Lurk has been built on top of. So Nova and Supernova are protocols that were introduced by Riyad Wabi and Srinath Sethi in late 2019, early 2020, no, late 2020, early 2021, and there are these folding schemes that allow you. And there's kind of a whole, I could say a lot about folding schemes. There's a whole ton of work around folding schemes, and there's a lot to say about it, but I won't, because